In this goal, we are going to learn about the relationship between energy and phase change. Recall what a phase change is. It's when you go from one phase to the next. So like melting, boiling, freezing, condensing. In melting, you're going from a solid to a liquid. In boiling, you're going from a liquid to a gas. Freezing is a reverse of melting, so going from a liquid to a solid. Condensing is a reverse of boiling, going from a gas to a liquid. Do you recall which two are missing? That's right, sublimation and deposition. In sublimation, it is going from a solid directly to a gas, and deposition is going from a gas to a solid. When we're looking at energy changes, we can draw what's called a heating curve. A cooling curve would just be the opposite, where you start from a gas and go to a solid. But in this heating curve, it looks very similar to the curve that we did in the lab for this unit. Notice that there are 5 distinct areas. So first of all, we have a solid, and then we have a flat line. In this flat line, this is our phase change. This is where we are going from a solid to a liquid. We're melting. And if you're going this way, you are going from a liquid to a solid. The next step is a liquid after you melt it. And after you heat a liquid, you have another phase change. You are boiling it, going from a liquid to a gas this direction, and the opposite direction, you're going from a gas to a liquid. This is a heating and cooling curve of water. When you're drawing these heating curves, the phase changes will always occur at a certain temperature. The boiling point of water is 100 degrees. And so I will draw a flat line representing the boiling point right at 100 degrees. The melting point for water is 0 degrees. So there's another flat line here. Recall with the phase changes, it levels off. And the reason why it does this is the energy is going into not making the molecule move faster or taking the energy out so it moves slower. Is the energy is going into breaking those intermolecular forces. So for water, in this case, it would be breaking that hydrogen bonding, dipole-dipole, and London dispersion. Hydrogen bonding is probably the strongest intermolecular force that's being broken there. So, and then you just connect the other areas. So we have right here our solid, and in this area we have our liquid, and this area here we have our gas. So, and again, the flat lines, these are our phase changes, and we will look at the boiling point and the melting point to help us draw these heating curves. So it's important that you mark those boiling point and melting points in these energy diagrams. When we are heating a solid or a liquid or gas, or we're going through a phase change, there is energy that is put into the system. If you're cooling things down, then there's energy taking out of the system. But this is the formula that you're going to use to determine the quantity of energy. And that's what our Q stands for. Q is energy in joules, or quantity of energy. M is mass. C is a constant. It's the specific heat constant. And all these units right here, they help transfer degrees Celsius and grams into joules, our energy unit. And then the last part of the formula is delta T. Delta T means change in temperature, and that is figured out by taking the final temperature minus the initial. Your delta T will have a negative value if you're cooling it off, and it will have a positive value if you're adding heat to your system. Later on the year, we are going to take and measure heat exchange with this formula, and we'll take a cup and we'll put in our water and our chemical, and we'll measure with the thermometer that heat change and solve for Q equals MC delta T. In your packet, you should have all these constants written down. And they have names that we're not familiar with, but I have put these constants in this order on your test. So you just need to know how to use them. So the specific heat of ice, we're going to use that when we are in our solid phase. The heat of fusion, this is when we are doing our phase change. So this would be melting or freezing, just depending on which way you go. If we're a liquid, we're going to use this specific heat of water. And if we're boiling or condensing, we are going to use this heat of vaporization. So they're all constants. It's just the phase changes. It goes by a delta H instead of just a C. And that last constant there is that's if you are heating a gas or cooling a gas down. So if you're putting heat into your system or heat into your water, that would be an endothermic reaction. And so the sign of that Q would be positive. If you are taking heat out, that means the heat is leaving the water. That means your Q will be negative. If you look at the delta H's or these phase changes, number one, notice how high they are. So in phase changes, again, the energy is not going into making the molecules move faster, but in breaking those intermolecular forces or reforming them if you're cooling them down. And it just takes time and it takes a lot of energy associated with those intermolecular forces. Notice that the heat of vaporization is our highest at 2,260 joules per gram. And what's happening here is your intermolecular forces are completely being broken. And so that takes a lot of energy. With melting, they are just breaking and then reforming. And so you don't break them all the way. If you've ever gotten burned with steam, you'll know that it's such a painful burn because there is so much energy in those vapor molecules when they hit your skin. Let's go ahead and do a sample math problem. Whenever you do these heating curve or cooling curve problems, you need to draw yourself a picture just so that you can keep clear which area of the 5 steps you're on. Sometimes you'll go through all 5 steps. Sometimes you just might do 1 step. Sometimes you might be 2 or 3. So draw yourself a picture to keep clear where you are. Most of the time, if you're heating from a negative to a number above 100, you're going to go through all 5 steps. And so you'll use all 5 constants here, or heats of fusion or vaporization. So in this problem, I'm going to take 100 grams of ice at negative 10 degrees Celsius, and I'm going to heat it all the way up to 110 degrees. So I'm going to go through all 5 different areas. Because I'm passing through 5 different areas, I will solve my Q equals MC delta T equation 5 times. Because there's something different going on in each of the phases. I'm going to first heat a solid, then melt it, then heat a liquid, and then boil it, and then heat a gas. So let's start with area A. In area A, we're heating our solid. So I'm in area A right here. Q equals MC delta T is our formula. My mass in each one of these is going to be 100 grams. And my constant is going to be the specific heat of ice, 2.06. And when I look at my graph, it's going to help me figure out the temperature. So I am starting at minus 10, and in area A, it stops at 0. So I am going to do final minus initial. And so I'll have 0 minus a minus 10. So that is just 10 degrees Celsius. And I didn't do a good job putting the units here, but they are important. I can cancel them out. So grams cancels and degrees Celsius cancels. For whatever reason, I didn't write it. All right, I wrote it, so that will cancel out. And let's just go ahead and do our math. So in our math, we have 2,060 joules. I'm not really doing sig figs with this problem, but you could do that, but save it for the last step. All right, so that's what's going on in my first area. So my first area stops at 0, and so that's as far as I can go. So the next thing I'm going to be doing is I'm going to be melting it. So this is a phase change, and because of this, we're going to change our formula just a little bit. Notice in a phase change, the temperature doesn't change, and because of that, we just drop it. So my formula changes a little bit. So it'll be Q equals MC, or if you wanted to call that constant a delta H, you could. It's the same thing. So we're going to have our 100 grams and multiply it by our heat of fusion, 334 joules per gram. I remember to do my units this time. And we're going to cancel out our grams, and we are left with 33400. Okay, so this is the amount of energy required to melt our sample. All right, no temperature change there, but we've gone all the way through melting, so now we're at a liquid. This is area C. So our formula is Q equals MC delta T. So we're back with our temperature changing because I can see it going from 0 to 100. So mass is 100 grams. Our specific heat of water is 4.18. And our change in temperature, remember, it's final minus initial. So my final temperature is 100. Area C stops at that temperature. I can't go past 100. So 100 is the final minus the initial, which is 0. So overall, a change in temperature of 100 degrees. So going the whole way from 0 to 100 on that area C, heating your water. And so my number will be 41800. Okay, so 41,800 joules. Okay. Next we have area D, and this is another phase change area. So remember, temperature doesn't change. So I just changed my formula by dropping the T. And I have 100 grams times the specific, or excuse me, the heat of vaporization. And so that would be 2260. And multiplying this out, I get 226000. So really a lot of energy is needed to boil that quantity of water. The last area is area E. So Q equals MC delta T. Mass is 100. And my specific heat of steam is 2.02. So my temperature change, I started at 100. I go to 110 in area E. And so final minus initial, 110 minus 100. I'm going up 10 degrees. We can multiply that out and we get 2020 joules. So what is the amount of energy required to go from minus 10 all the way to 110? Well, you have to do all 5 steps because 5 different things are happening and they have different constants associated with each of them. And so you have to do each of the steps, and then at the end, you're going to add them up. So when I add them up, I get 305,000 joules. Okay, rounded to 3 sig figs. So a lot of energy to take and go from ice all the way to heating up steam. So let's do a few more just so that you can kind of see what you need to do. The first thing you're going to do is you're going to draw yourself a picture. So a heating and cooling curve. Start here at the bottom. You're going to flat line, go up a little bit, and then flat line again, and then go up. Right where those little flats are, those are your melting and boiling points. So this is water, so I know that my melting point is 0 and my boiling point is 100. Let's go ahead and do this problem, figure out where we are. So how much energy is lost? Okay, so heat is going to be leaving if 50 grams of water is cooled from 75 degrees to minus 20. So on my graph, I'm just going to mark where I am. So I have 75 here, and I'm going to go all the way to minus 20. So what areas am I going to go through? Well, I'm going to go through this liquid area, then I'm going to freeze it going this way, and then I'm going to go through this solid area. So 3 different areas on our cooling curve. And I didn't really write it backwards. I just kept the heating curve and then just moving backwards. But it's just a guide. So we're in our first area. So in your packet, this would be labeled area C. And I use my formula, Q equals MC delta T. And I can fill in. So this time I have 50 grams. And my constant for this water area is 4.18. And then my temperature goes from 75 to 0 because this area ends at 0. So that's the maximum I can go. Now the heat is leaving, so final minus initial. So my final is 0 minus 75, so that's a negative 75. So this is going to be how much energy is going to be leaving. And when I do my math here, I get 15675 joules. And the negative sign just tells you the direction. So this is how much heat is lost in that first step. My second step is a phase change. So I do not need the temperature. So I have 50 grams times 334 joules per gram. And when I multiply that out, I get 16700 joules. Okay, so here's my first number. There's my second number. And even though it doesn't work out this way, this heat is leaving, so it is a negative number. Let's do our last area. So we've gotten to 0 degrees. Now we're going to make the molecules move slower, and we're going to cool off that temperature of the ice. So Q equals mc delta T. My mass is 50. This area has a constant of 2.06. And my change in temperature, I'm at 0. I'm going to go to minus 20. So minus 20 minus 0. So it's a negative 20. Multiplying this out, I get 2060, and it's a negative, meaning it's leaving. And my final step is to add all of these. So I'll add each one of these up, and that will be my final answer. They're all negative, and I end up getting a negative 34,435 joules. Okay, I didn't really do sig figs in this problem, but we can look at it. It looks like our lowest one is, I'll cheat a little bit and put a 0.0 right there, is 3 sig figs. So let's keep it at 3 sig figs. So minus 34400 joules was our final answer. Okay, so again, going through 3 areas. So I'm cooling down my liquid. It stops at 0. And then I'm going to freeze it. So that's my phase change. Temperature doesn't change. I'm just forming the crystal lattice of the solid. And then I'm going to cool the solid down. So 3 areas it goes through, 3 steps, and you add them up to figure out, in this case, how much heat leaves. Let's go ahead and do the last one. So how much energy in joules is needed to boil 50 grams of water? And I'm going to put 3 sig figs to begin with, okay? So we need to identify what area we're in. So I'm just going to sketch out my little heating curve. So, and again, I know this one's 100 here, and it's 0 here because that's my boiling point and my melting point. And where are we? How much energy is needed to boil? Oh, that's all it's asking. It's just boiling. Well, this is boiling right there. So this is a one-step problem. So it's a phase change, so there's no change in temperature. So my mass is 50 grams multiplied by that heat of vaporization. And if you look, the units for your heat of vaporization, there's no degrees Celsius there. So it kind of gives you a clue that there's no temperature. All right, multiplying this out, I get 113,000. So, and this is a positive number because I'm putting this heat in, and this is joules. So that's my final answer.